This is the fifth lecture on NMR. In this lecture, we will discuss about the integration of signals, which indicates the number of protons which are giving a particular signal. And second is the spin-spin coupling, which gives us the information regarding the number of protons present on the neighboring carbon atom. This is the NMR spectrum of benzyl acetate. This spectrum shows three signals: one signal at delta 2.0, second signal at delta 5.0, and the third signal at delta 7.2 value. It means to say that in benzyl acetate, there are three different types of protons are present. Now the question is how we can determine the number of protons giving a particular signal. So in NMR it is said that the area under the peak is directly proportional to the number of protons generating that signal. So area under the peak can be determined by the integral present on that particular peak. We can observe three integrals. One integral which is present at the signal delta 2.0. Second integral is present on the signal which is seen at 5.0, and the third integral which is seen at the signal which is present at delta 7.2. On the chart paper we can see that the integral which is present at the signal 7.2 corresponds to 55.5 divisions, and the integral which is present at the signal which is seen at 5.0 delta value corresponds to 22.0 divisions, and the third integral which is seen at the signal which is present at delta 2.0 corresponds to 32.5 divisions. Now each larger number is divided by the smallest number, and by doing this we will get the relative number of protons which is giving particular signal. So 55.5 divided by 22 gives 2.52, 22.0 divided by 22 gives 1.0, and 32.5 divisions divided by 22.0 gives 1.48. This is the relative number of protons giving three different signals. Now it can be multiplied by 2 and the values are round off. So the ratio becomes 5:2:3. It means to say there is one signal, this one which is seen at 7.2 delta is given by 5 equivalent protons, and the signal which is seen at delta 5 is given by 2 equivalent protons, and the signal which is seen at delta 2.0 it is given by 3 equivalent protons. So by knowing the integral height of the integral, we can determine the relative number of protons giving signals. The modern NMR spectrometers gives the digitized integral values for the integrals. In this spectrum, these digital integral values are given below the signal. So the values are 58.117, 33.929 and 21.215. Now again the same procedure is adopted, that the larger values are divided by the smallest number, and this gives the relative ratio of protons which are giving the signal. The ratio comes out to be 2.52:1:1.48. Again this is multiplied by 2 and gives the ratio 5:2:3. So there is a signal because of 5 equivalent proton, another signal because of 2 equivalent proton, and the third signal because of the 3 equivalent proton. So this is the NMR spectrum of benzyl acetate which is recorded on the modern NMR spectrometer, It is recorded at 300 MHz FT-NMR. So there is no need to calculate the number of divisions from the chart, but digitized integral values are given from which we determine the relative number of protons giving a particular signals. Another method for determining the area under the peak is by measuring the height of integral. For example, in this NMR spectrum, there is one signal close to 3 delta value and another signal is seen close to 5 delta value. And on each signal, there is one integral is present. By scale, the height of these integrals are measured. So the integral which is present at the signal 3 is 41 mm and the integral which is present close to 5 signal is 16 mm. And it is given that this NMR spectrum is given by a compound for which the molecular formula is C2H4Cl2. From this data, we can determine the height corresponding to one hydrogen atom. For this, we will add up the height of two integrals, that is 16 mm plus 41 mm, and we will divide it by number of protons, that is 4. So 14.25 mm is the height corresponding to one hydrogen atom. Now from this value, we can determine the number of protons giving a particular signal by dividing the height of integral. So 16 mm is divided by 14.25, it gives 1.12, that is approximately 1 proton, 1 hydrogen. That is, this signal which is close to 5 is given by only 1 hydrogen. And 41, when it is divided by 14.25 mm, it gives 8.8, 2.88. That is approximately 3 hydrogens. That is, the signal which is present at the 3 delta value is given by 3 equivalent protons. So, in the formula it is given that there are 4 protons. In this, from the data, we have concluded that the one signal given by 3 equivalent protons and one signal is given by 1 proton. So in this manner, we can also calculate the area under the peak and the number of protons giving a particular signal. Another phenomena in NMR is spin-spin coupling or spin-spin splitting. This phenomena results in the splitting of the signal. For example, look at the NMR spectrum of trans-cinemic acid. Cinemic acid is C6H5CH double bond CH-COOH. Cinemic acid is trans here because Ha proton and HX proton is trans to each other. From our previous experience, we can predict that this compound will show 4 signals in its NMR spectrum. One signal because of the 5 equivalent aromatic protons, and the signal will be seen close to 7.5 delta value. The carboxylic proton, which is highly de-shielded proton, the signal will be seen out of the scale. The resonance value for this is 12.5 delta value. The resonance value for Ha proton is 6.4 and the signal of HX proton is centered at 7.8 delta value. Now observe the signal from Ha. It is not a single line, but there are 2 peaks. That is, the signal splits up into 2 peaks. Similarly, the signal of HX proton also splits up into 2 peaks. So this phenomena occurs because of the spin-spin coupling, and this leads to splitting of the signal. That's why the name is spin-spin splitting, and it is also known as spin-spin coupling. The spin-spin coupling, it is not the space phenomena, but the two neighboring proton interacts, they couple with each other through the intervening covalent bonds. The number of peaks in a signal depends upon the number of protons present on the neighboring carbon atom. The general rule says it is n plus 1 peaks. That is, the signal of a particular proton will split up into peaks, different peaks, depending upon the number of protons present on the neighboring carbon atom. If the number of protons on the neighboring carbon atom is n, then the signal will split up into n plus 1 peaks. Now, the space between the peaks is known as the coupling constant J. And this is the coupling constant J for HA proton, that is the spacing between the two peaks. Similarly, the spacing between the two peaks in case of the signal of Hx is also the coupling constant J. Observe that the value for the coupling constant J is same for HA and Hx, and this indicates that the proton HA is coupling with the proton Hx. This is the NMR spectrum of 112 trichloroethane, which is recorded at 80 MHz in CdCl3. From the structure of 112 trichloroethane, it is very clear that this compound will show two signals in its NMR spectrum. One signal because of methane proton and one signal because of the two methylene protons. Methane proton will be more de-shielded as compared to methylene protons because it is present on the carbon atom which is bonded to two chlorine atoms. And these two chlorine atoms will show twofold minus I effect, and the electron density on methane protons will be very, very low, and therefore methane proton will be more de-shielded as compared to methylene proton, where only one chlorine atom is present. So this is the signal because of methane proton, which is seen close to 6 delta value, and the signal from methylene proton is seen at delta 4 value. Now see, the signal because of the methylene proton splits up into two peaks. So the neighboring of the methylene proton is only one proton, and therefore it splits up into two peaks. Whereas the signal from the methane proton splits up into three peaks because methane proton has got two neighbors. So again we can apply n plus 1 rule. N is the number of neighboring proton. So if the number of neighboring proton here in case of this compound is 2, and therefore the signal of methane proton splits up into 3 peaks. Whereas the neighbor of methylene proton is only one proton, therefore the signal of methylene proton splits up into two peaks. We have already seen the NMR spectrum of cinemic acid, and we have observed a doublet for proton A and a doublet for proton X. That is to say, proton A and proton X shows resonance two times. So the question is why this happens. To understand this, take the example of proton A first. The resonance frequency depends upon the total magnetic environment around proton A. The total magnetic environment also includes its neighbor proton X, which itself it is a magnet. So the nuclear magnet of proton X can be aligned with proton A, or it can oppose proton A. When it is aligned with proton A, so the net effective magnetic field will be greater at proton A, and when proton X is aligned against proton A, then the total net effective magnetic field will be slightly less. It will feel the decreased effective magnetic field. So proton A will resonate two times. One, when the net effective magnetic field is increased, and when the net effective magnetic field is decreased. In other words, we can say that the proton A can be de-shielded because of the spin orientation of X, and it can be shielded because of the spin orientation of proton X when it is opposing proton A. So the proton A will show the two resonance frequency. Similarly, we can explain a doublet from proton X also. The total magnetic environment of proton X also includes its neighbor proton A. The nuclear magnet of proton A can align with proton X, or it can oppose the proton X. That is to say that proton X can be de-shielded or it can be shielded. At one point of time, when the nuclear proton A is aligned with the proton X, then the effective magnetic field will be greater and proton X will be de-shielded. And when the nuclear magnet of proton A is opposing the proton X, then the effective magnetic field will be slightly less and proton X will be shielded. So in these two situations, it will show two different resonance frequency, and the signal will be a doublet. It will split up into two peaks. So the presence of neighboring proton can shield the proton or it can de-shield its neighboring proton. So the signal will split up into two peaks. We can represent different spin orientations of two coupling proton by this diagram. Proton A and proton X are neighboring proton and they are coupling with each other. Suppose proton A is showing the absorption and its neighboring proton X can have different spin orientation. The spin orientation can be parallel or spin orientation can be antiparallel. Parallel spin orientation is represented by alpha and antiparallel spin orientation is represented by beta. When proton A is showing the absorption and the spin orientation of proton X is parallel, in this condition, the net effective magnetic field on proton A will be slightly higher and proton A will be de-shielded. When proton A is showing the absorption, but the spin orientation of proton X is antiparallel, in this condition, the net effective magnetic field on proton A will be slightly low and the proton A will be shielded. That is to say, because of the two different spin orientation which proton A can see, it will show resonance two times. One, when the net effective magnetic field is slightly higher, and second resonance is when the net effective magnetic field is slightly low. So a singlet will split up into two peaks. The distance between the two peaks is known as the coupling constant J. In the same manner, we can show the splitting of proton X by the different spin orientation of proton X. Now proton X can see two different spin orientations of proton A. One is parallel, another is antiparallel. When proton A spin orientation is parallel, in this condition, the net effective magnetic field on proton X will be slightly higher and this proton will be de-shielded. And when the spin orientation of proton A is antiparallel, in this condition, the net effective magnetic field on proton X will be slightly low and proton X will be shielded. So proton X will also show two different resonance states. One when the net effective magnetic field is greater, another when the net effective magnetic field is low. So the signal of proton X will also show two peaks, and the distance between the two peaks will be known as the coupling constant G. Here you see the intensity of the two peaks is equal. It is 1:1. Spin-spin coupling is not a field phenomena, but it occurs through the intervening covalent bonds. The two coupling protons HA and HX. So they mutually couple with each other. So their signal splits up into two peaks. A doublet is seen for proton A and proton X. The nuclear spin of proton A couples with electron spin of carbon proton A electrons, and this is transmitted to carbon-carbon bond. So it couples with carbon-carbon bonding electrons, then it couples with carbon proton X electrons, and finally it is transferred to spin of proton X. So we can say that the spin-spin coupling is transmitted from one proton to another proton through the intervening covalent bonds. So here proton A to proton X, there are three intervening covalent bonds, 1, 2, 3. So the coupling constant between proton A and proton X will be known as J3 coupling. Consider the spin coupling between proton A and two neighboring proton X. That is the AX2 spectrum. Proton A is showing the absorption and there are two protons X. They are represented by X and X prime. There can be three different possible combinations of spin. One is when both the protons have the parallel spin. That is, both are alpha-alpha. Another condition is when the spin orientation of both the protons is antiparallel. That is beta-beta. And the third spin combination is when one proton, that is X, has a parallel spin and X prime has the antiparallel spin. Then X has a antiparallel spin and X prime has a parallel spin. So because of the three different possible combination of spin, there are three distinct energy situations. So the proton A will show the absorption three times. It will have three resonance frequencies and the signal will split up into three peaks. And the ratio of the three peaks will be 1:2:1. This condition is represented by example 1,1,2-trichloroethane. This is the NMR spectrum of this compound. There is a signal because of the methene proton and there is a signal because of the methylene proton. Two methylene protons will couple with one methene proton and the signal of methylene proton will split up into two peaks and the ratio of the two peaks will be 1:1. Whereas the methene proton will couple with two neighboring methylene protons and the signal of methene proton will split up into three peaks and the ratio of the three peaks will be 1:2:1. And in this manner, we can explain the combination of AX2 spectrum. Consider the spin coupling between proton A and its neighboring X proton, which are 3 in number, and this type of spectrum is known as AX3 spectrum. The 3 neighboring X protons are designated as X, X prime and X double prime. Proton A can see different spin orientations of 3 neighboring protons. One situation is when the 3 neighboring protons has parallel spin orientation. Second situation is when the 3 neighboring protons have antiparallel spin orientation. The third situation is when the 2 neighboring X protons have a parallel spin orientation and one neighboring X proton has antiparallel spin orientation. And this can happen in 3 different manners. The fourth situation arises here is that 2 neighboring X protons have antiparallel spin orientation and one proton has parallel spin orientation, and this situation can also arise in 3 different manners. So the proton A can see 4 different energy situations. So it will show the absorption at 4 energy levels. So a singlet from HA proton will split up into 4 peaks, and the intensity of these 4 peaks will be 1:3:3:1, and the distance between the peak will be known as the coupling constant J. So the proton A, which has got 3 neighbors, the signal of proton A will split up into 4 peaks. That is n+1 rule. It has got 3 neighbor protons, so the signal will split up into 4 peaks. N is equal to 3 plus 1, it is 4. And the intensity will be 1:3:3:1. NMR spectrum of alpha chloropropanoic acid indicates AX3 type of spin-spin coupling. In alpha chloropropanoic acid NMR spectrum, we will observe 3 signals. One signal because of the acidic proton, and we know that the acidic protons are highly de-shielded proton, and the signal is seen close to 12 delta value, that is out of the scale. Signal because of the methene proton is seen at 4.5 delta value. This methene proton is also de-shielded proton because of the presence of chlorine atom. Chlorine atom, due to -I effect, withdraws the electron and proton becomes de-shielded. Similarly, there will be a signal because of the 3 equivalent methyl protons, and the signal is seen close to 2 delta value. Now look at the spin-spin coupling between methene and the 3 equivalent methyl protons. Methene proton will see 3 different spin orientations from 3 equivalent methyl protons, and the signal of methene proton will split up into 4 peaks. The intensity of the 4 peaks will be 1:3:3:1. Similarly, methyl protons will see 2 different spin orientations of methene proton, and its signal will split up into 2 peaks, and the intensity of the peak will be 1:1. So this is a very clearly shows that the spin-spin coupling between methyl protons and one methene proton. Now look at only the NMR spectrum. Don't look at the structure of alpha chloropropanoic acid. If we don't have the structure here, but we have the NMR spectrum, and by looking at the splitting pattern, we can predict the number of neighboring protons. Now this signal has got split it up into 4 peaks. It means to say that neighboring protons of methene will be 3 in number. here we will apply n-1 rule. Look at the 4 peaks of this signal, and it has split up into 4 peaks because there would have been 3 neighboring protons. So when we look at the NMR spectrum, then we apply n-1 rule. Similarly here, there are 2 peaks, means to say that its neighbor will have only 1 proton, that is n-1 rule. So when you see the structure and you want to predict the splitting of signal by looking at the structure, in that case we apply n+1 rule. And when we see the spectrum and we want to determine number of protons on the neighboring carbon atom, then we can apply n-1 rule. This is the Pascal's triangle, and from this Pascal's triangle we can predict the intensities of the peaks in multiplets. If there is no neighboring proton, then only a singlet will be seen. If there is one neighboring proton, there will be 2 peaks. For 2 neighboring proton, there will be 3 peaks. For 3 neighboring proton, there will be 4 peaks. For 4 neighboring proton, there will be 5 peaks. And for 5 neighboring proton, there will be 6 peaks. So the relative intensity of the peaks can be predicted by Pascal's triangle. For the construction of Pascal's triangle, the intensity of the outer peaks is always taken as 1. The intensity of the inner peak is calculated by adding the 2 numbers present immediately above that number. For example, if there are 2 neighboring protons, then signal will split up into 3 peaks. So the intensity of the outer peak will be 1 and 1. For the inner peak, for 2, we will look at the numbers which are present immediately above this, and we will add up the number which is present on the right hand side and the left hand side. The right hand side it is 1, left hand side it is 1. Add up the 2 numbers, so it will come 2. So in a triplet, the relative intensity of the peaks will be 1:2:1. Take another example. Suppose there are 4 neighboring protons, then the signal will split up into 5 peaks. That is, a quintet will be seen. 1, 2, 3, 4, 5. So the relative intensity of the outer peaks will be 1 and 1. For the inner peaks, we will look at the above number. At the right hand side it is 3, on the left hand side it is 1. Sum the 2 numbers, so 3 plus 1 is 4. For another peak, right hand side is 3, left hand side is 3, so the intensity will be 6. Then right hand side is 1 and left hand side is 3, 3 plus 1 is 4. So in a quintet, the multiplicity will be, it is 5, and the relative intensity will be 1:4:6:4:1. So in this manner, you can extend the Pascal triangle and we can determine the relative intensity of the peaks from this triangle. Presence of ethyl group can be predicted from NMR spectrum. Look at this spectrum, and there is a combination of quadrate and a triplet. This is the quadrate and this is the triplet. The triplet shows the presence of 2 neighboring proton and the quadrate shows the presence of 3 neighboring proton. So by this we can predict the presence of ethyl group. Observe one more characteristic of this spectrum, that inner peaks are larger than the outer peaks. In a quadrate, we have seen that the intensity of the peaks will be 1:3:3:1. And in a triplet, the intensity will be 1:2:1. But in a quadrate, the two outer peaks, which should be 1:1, but the inner peak is slightly larger than the outer peak. Similarly, in 1:2:1 peak ratio, intensity ratio, the inner peak is slightly larger than the outer peak. And this is a very good indication for predicting which two protons are coupling with each other. In the NMR spectrum of larger molecules, too many signals are seen. Then it becomes difficult to predict which protons are coupling. We can show that which protons are coupling by drawing arrows on the multiplets. The arrows are drawn from the outer peak, which is smaller, towards the larger peak. So this is a combination of quadrate and triplet. On quadrate, this is the inner peak, which is longer than the outer peak. So arrow will be drawn from the smaller outer peak towards the longer inner peak. Similarly, on a triplet, an arrow is drawn from the shorter peak towards the longer peak. Now this arrow indicates towards this quadrate and this arrow indicates towards this triplet. And this also shows that the proton to which it is coupling are downfield to these protons. And the proton coupled to this quadrate is upfield. So proton B are downfield and proton A are upfield. So by looking at the direction of arrow, we can predict which protons are coupling and in which direction they are present. This is the NMR spectrum of 3-methyl-2-butanol. There are three signals, A, B and C. Signal A is because of these three equivalent methyl protons. Signal B is because of these 6 equivalent methyl protons, and signal C is because of this methene proton. Signal A, it is a singlet because there is no protons present in the neighboring carbon atom with respect to this methyl protons. So it is a singlet. 6 equivalent proton gives signal B, which is a doublet due to the spin-spin coupling with the methene proton. And the methene proton, which gives signal C, it's a septate because its neighbor has got 6 equivalent proton. So it is a septate. So it is clearly indicating the spin-spin coupling. So from this NMR spectrum, we can predict the number of neighboring protons and how the multiplicity will take place. This is the NMR spectrum of 1-nitropropane. There are 3 signals. One signal is because of the methyl protons, which is present at delta 1 value. Second signal is because of the central methylene proton, which is present at 2 delta value. And the third signal is again because of methylene protons, which is present at 4.5 delta value. Methene protons, which are close to nitro group, are de-shielded protons because of the presence of nitro group. Nitro group, it is an electron withdrawing group. Therefore, methene protons are de-shielded and the signal is seen at delta 4.5 value. Now look at the splitting pattern. The signal from the methyl proton is a triplet because of the presence of neighboring 2 methylene protons. So a triplet is seen. The intensity of the peak is 1:2:1. But look at here, the inner peak is slightly longer than the outer peak. Similarly here, see the splitting pattern of methylene proton, which are bonded to nitro group. It is again a triplet because the neighboring carbon contains 2 proton here, and the signal splits up into 3 peaks. Again the ratio is 1:2:1. The inner peak is slightly longer than the outer peak. The central methylene proton couples with 3 methyl protons and 2 methylene protons. That is, the central methylene proton has got 2 neighbors, 3 methyl protons and 2 methylene protons. That is, the total number is 5. So n is 5 plus 1 is equal to 6. So the signal of central methylene proton will show a sextate here. So this is the sextate of central methylene proton. So how the sextate is obtained? First, the central methylene proton will couple with the 3 methyl proton. So 4 lines are seen, and the distance between these lines is known as the coupling constant J between CH3 and CH2. Now the central methylene proton will again couple with the methylene proton, which is bonded to nitro group, and every line will split up into 3 peaks. Since the coupling constant JCH2CH2 and the coupling constant JCH3CH2 is identical, therefore overlapping of peaks will be seen, and ultimately it will result into a sextate.